Hello, I want to go over chapter number 4 and review some of the topics. I believe that details you see here can better prepare you for assessment. The first thing is that we have only 118 elements in the periodic table. However, the variety of compounds that we can find is really big. In this course, you have watched previous videos about the composition of matter, how we have pure substances and mixtures. In this chapter, you will better understand how elements are represented by symbols in the periodic table, and later how atoms combine to make thousands of substances. First, we need to master the meaning of those little numbers around those symbols of elements. We need to understand their position in columns that we call groups and rows that we call periods. Atoms are particles that are composed of three subatomic particles, the proton, the neutron, and the electron. When atoms combine, they form compounds. A compound has more than one type of element. For example, sodium chloride is a compound made of opposite charges, sodium plus and chloride minus. Molecules can be gases like ammonia, can be liquid like water, or they can be solid like aspirin. According to Dalton's atomic theory, atoms are tiny particles of matter. Atoms of an element are similar to each other and different from those atoms of other elements. Atoms of two or more different elements can combine to form compounds. Atoms rearrange to form new combinations in a chemical reaction. Atoms are never destroyed during a chemical reaction. The atom is in the center where we find the nucleus. The nucleus is made of protons, which carry a plus charge, and neutrons that have no charge. The vast majority of the atom is empty space that we call the electron cloud. This is where we have electrons, negatively charged particles. The mass of the electron, when compared to the mass of the proton, is so small that can be considered as zero. The actual value of the mass of the proton and the neutron is 1.007 atomic mass unit, and when it is one atomic mass unit is equal to 1.6 10 to the negative 24 grams. That is so small that it's better to use the values of +1. Now the mass of the electron is 10 to the negative 28. Because atoms are neutral, the number of protons and electrons are the same. For example, we have here carbon, that is atomic number 6. That atomic number represents the number of protons, that is 6 protons, and because these atoms are neutral, it will have 6 electrons. An atom is electrically neutral. Like charges repel and opposite charges attract. There are as many negative charges, electrons, outside the nucleus as there are units of positive charges or protons inside the nucleus. The mass of neutrons and protons are called the atomic mass unit, which is measured using carbon as a standard, which is 1/12 of the mass of carbon. The mass of an electron is so small that we can say that it is neglected. Protons are positively charged, electrons are negatively charged, and neutrons are no charged. The electrons repel each other because they have like charges, but are not separated from the atom because they are attracted to the nucleus positive charges. The chemical reactions to create different substances don't involve the neutrons. We care a lot more about the number of electrons. For example, aluminum has 13 protons. From there, we know it has 13 electrons, from which it has 3 electrons that are available for reactions. Those are the electrons that we call to be in the outermost shell. Of course, neutrons and protons participate only in nuclear reactions. We need to get familiar with the numbers that are written around the symbols of the element. A symbol could have one letter like hydrogen, or it could have two letters like sodium that has Na. Always remember that the symbols of the elements start with a capital letter. It's not okay to put a small letter for the N of sodium here. Also remember that the atomic number represents the number of protons. The number of protons will not change in a chemical reaction. The number of protons will be equal to the number of electrons in the neutral atom. We also know that we have the mass number, which represents the number of protons plus the number of neutrons. For example, we know here that beryllium atomic number is 4, so I know from there that it has 4 protons and 4 electrons. Potassium atomic number is 19. It has 19 protons and 19 electrons. I need more information to know what is the mass number because I don't have the information of how many neutrons you have. Not always the number of protons will be identical to the number of neutrons. That number varies. Mention, not necessarily the number of protons and neutrons will be identical. For example, we have phosphorus that has an atomic number of 15, and I have the information here that it says that it has 15 protons. Of course, it will have 15 electrons, but in this case, we see that it has 16 neutrons. Oxygen has 8 protons, 8 electrons, and in this case, it will have also 8 neutrons. Now, we have titanium that has 22 protons, 22 protons plus 26 neutrons to make an atomic number 22 and a mass number of 48. In future assessments, you will be asked to calculate number of protons, number of electrons. I will give you a box in a worksheet, so you will complete tables using formulas like this. You have to calculate number of protons or neutrons. If I give you one piece of information, you can get the rest. But in this slide, I also want to show you that we have some elements that will have more than one type of atoms. Let's say we'll have the same number of protons but different number of neutrons, and that is what we call isotopes. They are atoms with the same number of protons but different number of neutrons, and for that we have some examples used from your textbook. Isotopes are atoms of the same element but they have different masses. I am showing you here hydrogen that has 3 different isotopes. The first one is called proton, which only has 1 proton and 1 electron. We have deuterium that has 1 proton, 1 electron, and 1 neutron. And we have tritium, which has 1 proton in blue, 1 electron, and also 2 neutrons. So they will have different masses, but they will have the same reactivity because the 3 of them will have 1 electron. The second example here is using titanium that has 1 isotope with 48 atomic mass number, and the second one is 50 because it has a different number of neutrons. I want to present a few more examples so you guys can practice. The first thing is that we have here oxygen 16 and oxygen 17. They are isotopes of each other. They have the same atomic number, which is 8. Atomic number 8 means that it has 8 protons for oxygen 16 and for oxygen 17. Because it has 8 protons, we know that atoms are neutral, so they have the same number of electrons. So both of them will have 8 protons and 8 electrons. Because they are isotopes of each other, they will have different masses. So oxygen 16 will have 8 neutrons and oxygen 17 will have 9 neutrons. The second example I have is for uranium. Uranium has 2 different isotopes. Uranium number 235 and 238. In 235, we have 143 neutrons, and on uranium 238, we have 146 neutrons. But the number of electrons and protons for both of them are the same. There is one more element that I'm presenting here from the periodic chart, and that is gallium, that has atomic number of 31. And then this number that we see here in fraction is the average of masses of the different isotopes that gallium will have. When you see that is a whole number, we are talking about what is how we call it, but the atomic mass that is on the periodic table represents a weighted average of all of the masses of all of the isotopes that are occurring naturally for each element. Here we have now magnesium, which has 3 naturally occurring isotopes. It has an atomic mass of 24.31 AMU. That is the number that we will read on the periodic table. The abundance is what you see here. We have 78.70, that's the very large block that we see, 10.13% and 11.17 for 3 different isotopes. So how do we come about with the number that comes on the periodic table? We're going to do some calculations during the health session, but I also want you guys to look at these ones. To calculate the average atomic mass, each exact atomic mass in atomic mass unit is multiplied by its percent abundance, which is expressed as a decimal. Then you will add the results together and round off to an appropriate number of significant figures. What we see here is we are dividing the percentage of abundance of magnesium 24, so that is 78.70 divided by the 100, multiplied by 23.99. You do the same for each one of the isotopes, and then you are going to add them up. A common mistake that I observe the students that have not prepared do in assessments is that instead of using the percentages given for different isotopes, they will add the exact masses in atomic mass unit and divide it by 2. That is not how that works. You have to always remember, use the percent of abundance. It's easy just to convert that to a fraction, multiply by the atomic mass unit of each one of the isotope, the corresponding one, then you just add them up. You don't have to divide by 2. And that is the end of the discussion for today.